The pursuit of space colonization has evolved from a philosophical dream into a layered, technically challenging endeavor that blends advanced astrophysics, engineering, societal adaptation, and economic planning. In this analysis, we examine the transformation of space colonization efforts, spanning from established plans for Mars to the more speculative prospects involving exoplanets. For an audience well-versed in planetary science and aerospace engineering, we delve into the interplay between theoretical models and applied research, exploring the granular details behind emerging strategies. Technical discussions center on propulsion advancements, atmospheric sciences, and closed-loop life support systems that support long-term human habitation beyond Earth. Moreover, our discussion illuminates how experimental data from recent robotic missions has refined our understanding of planetary geology and climate, informing habitat designs that account for extraterrestrial gravitational and radiation environments. A critical examination of the evolution of this field reveals a complex matrix of geopolitical interests, international partnerships, and bold private sector investments, all undergirded by robust computational simulations and iterative design methodologies. Here, we connect seminal historical milestones with present-day innovations in propulsion physics and bioregenerative life support systems, scrutinizing the intricate balance between resource extraction and sustainability. In sum, this presentation not only recounts past achievements but also rigorously analyzes upcoming challenges and opportunities that include interplanetary travel time optimization, fuel resource allocation, and advanced mission planning through real-time telemetry integration. By delving into technical details and numerical analysis, we aim to provide an informed platform for further discussion, paving the way for future paradigms in the collective effort to establish humanity's foothold among the stars. This discussion brings together rigorous theoretical frameworks and empirical data, providing insights into mass driver propulsion, nuclear thermal rockets, and other advanced technologies that underpin the grand challenge of off-world settlement. Our presentation synthesizes decades of research, policy debates, and innovative engineering approaches. To fully appreciate the journey of space colonization, it is essential to trace its historical roots and understand the milestones that paved the way for modern exploration. Early poetic visions of cosmic habitation emerged during the Enlightenment, when writers and scientists alike imagined celestial colonies as symbols of human progress and destiny. From speculative essays in the 17th century to the imaginative science fiction of the 19th century, foundational ideas provided inspiration for practical scientific inquiry. As the 20th century advanced, geopolitical tensions and rapid technological development converged in the space race, igniting a fervor for extraterrestrial exploration. Government-funded programs, such as NASA and the Soviet Space Initiative, not only launched the first satellites and manned missions, but also established research traditions that continue to resonate. Iconic missions like Apollo, Luna, and Vostok offer tangible proof of humanity's early determination to reach beyond Earth's confines. These early projects underscored key lessons in project management, resource allocation, and risk mitigation, forming the building blocks for more ambitious colonization proposals. Public sentiment gradually shifted from shock and awe towards measured curiosity about living off-world. Enthusiasm was driven by the development of rocketry and space technology that transitioned theoretical musings into proven technological pursuits. Over the decades, consistent investment in aerospace research fostered an environment ripe for testing ideas that once belonged only to the realms of fantasy. In addition, the Cold War rivalry further accelerated milestones by creating a competitive atmosphere that guaranteed continuous funding and innovation. This historical evolution, marked by both triumphs and setbacks, laid the technical, political, and cultural foundations currently influencing space colonization. Each successive breakthrough built upon the last, forming a legacy of collaborative effort between scientific communities and national governments, and setting the stage for more complex projects, such as sustaining human life on Mars and beyond. By examining historical records and mission data, researchers have also uncovered key insights into the evolution of spacecraft design, communication systems, and planetary protection measures. These findings continue to inform current strategies, merging historical precedent with modern innovations to chart a sustainable path forward in space colonization with precision. Among all the destinations for humanity's interplanetary expansion, Mars stands as the most thoroughly studied and technologically feasible candidate. Mars colonization has been under active consideration since the mid-20th century, with detailed assessments of its atmosphere, soil composition, and water ice reserves. In recent years, advances in remote sensing, atmospheric modeling, and robotic technology have greatly enhanced our understanding of Mars' environment. The planet's gravity at about 38% of Earth's is a substantial challenge for long-term human physiology, while its thin carbon dioxide-dominated atmosphere and high radiation levels necessitate robust habitat shielding and advanced environmental control systems. Key missions, including NASA's Viking landers, Mars rover expeditions, and international missions like the ExoMars program, have contributed vast amounts of empirical data. These missions have not only mapped the Martian surface with unprecedented precision, but have also analyzed soil samples, characterized dust storms, and helped simulate in situ resource utilization (IAU) techniques. The insights gained from these missions influence designs for future human habitats, such as inflatable modules, regolith-derived construction techniques, and nuclear-powered energy systems. Ongoing initiatives employ computational simulations to fine-tune landing strategies, orbital insertion parameters, and long-term climate models, while addressing technical challenges from thermal regulation to radiation exposure. Proposals for Mars bases incorporate closed-loop life support systems capable of recycling water and oxygen, demonstrating the potential for self-sustaining colonies. Furthermore, recent studies have detailed the economic and resource allocation models required to establish and maintain a colony, such as the cost-benefit analysis of developing propellant production facilities on Mars. Notably, Mars colonization plans also incorporate contingency strategies to manage the risks posed by solar particle events and meteorite impacts. Engineering teams collaborate internationally to design infrastructure that can adapt to varying Martian conditions, including seasonal dust contamination and thermal fluctuations. Direct comparisons with lunar colonization have reinforced Mars' potential for both scientific discovery and eventual human settlement, given its rich geological features and historical water activity. In closing, the journey toward Mars colonization rests on a foundation of rigorous scientific data, detailed engineering studies, and decades of mission experience, charting a precise roadmap toward humanity's future interplanetary ultimate home. Extensive analog testing on Earth, utilizing desert and polar environments, has contributed critical validation of Mars habitat designs and energy management systems. These experiments, combined with high-fidelity simulations, underscore the importance of redundant safety protocols and statistical risk analyses, ultimately advancing mission readiness for real-world application, ensuring robust operational success. Beyond Mars, other celestial bodies in our solar system present unique opportunities and challenges for colonization. The Moon, with its proximity, offers a natural proving ground for sustainable off-world settlements, albeit with its own extreme thermal cycles and regolith hazards. Similarly, asteroids and the Moon's orbiting gas giants such as Europa and Titan provide abundant resources, from water ice to rare minerals, through processes like mining and in situ resource extraction. Each of these locations demands specialized engineering adaptations and environmental considerations. For instance, lunar habitats must contend with substantial temperature fluctuations ranging from about 973 degrees Celsius during lunar night to 127 degrees Celsius in daylight, while asteroid bases benefit from microgravity environments, but require innovative anchoring and mining techniques. Moons like Europa challenge the design of radiation shielding and subsurface exploration systems due to thick ice layers concealing potential oceans. Titan, with its dense nitrogen-rich atmosphere and liquid hydrocarbon lakes, presents a completely distinct ecosystem, requiring novel life support and mobility solutions. Future mission concepts are leveraging robotics, artificial intelligence, and autonomous resource processing to simulate potential colonization scenarios. In-depth studies of these celestial bodies utilize remote sensing, spectral analysis, and advanced computer models to assess their habitability. For instance, lunar regolith simulants are instrumental in testing construction techniques, while Europa's ice-penetrating radar data stimulates discussions on subsurface exploration technologies. Through continuously evolving mission architectures and rigorous pre-deployment testing on Earth analogs, researchers develop strategies that can adapt to diverse extraterrestrial conditions. Analytical models quantify the trade-offs between on-site resource utilization and Earth-supplied infrastructures, thereby optimizing logistics and long-term sustainability. This multifaceted exploration underscores the importance of integrating cross-disciplinary expertise to overcome environmental constraints while capitalizing on the inherent resources of our solar system. By synthesizing lessons learned from lunar explorations, asteroid prospecting, and the study of icy moons, we draw critical comparisons that highlight the necessity for flexible module designs, scalable energy systems, and autonomous maintenance solutions. These collective endeavors further refine our strategies for leveraging available resources, ensuring that future settlements remain resilient in the face of unpredictable extraterrestrial challenges. This synergy promotes lasting, sustainable, and innovative colonization models globally. Recent astronomical surveys have uncovered thousands of exoplanets, many of which reside within their star's habitable zone, where liquid water could potentially exist. These discoveries, facilitated by missions such as Kepler, TESS, and Cheops, have expanded our understanding of planetary diversity and the potential for life beyond the solar system. Detailed spectral analysis and transit photometry provide essential data, revealing atmospheric compositions, orbital dynamics, and clues to geological activity that inform our models of habitability. For experts, the challenges of exoplanet colonization are particularly intriguing. The vast interstellar distances necessitate propulsion systems far beyond current chemical rockets, with theoretical models exploring nuclear pulse propulsion, antimatter drives, and warp field concepts. Such propulsion systems require detailed analysis of energy thresholds, relativistic mass effects, and the integration of artificial intelligence in real-time navigational corrections. Contemporary studies employ high-resolution simulations and quantum-limited sensors to predict environmental conditions on these distant worlds, ensuring that mission designs can accommodate extreme variability in stellar radiation and cosmic ray flux. In parallel, advanced astrobiological research seeks biosignatures and chemical markers indicative of life. Cutting-edge laboratories simulate exoplanetary atmospheric chemistry, and data from space telescopes refine our understanding of planetary albedo, magnetic field interactions, and climate feedback mechanisms. Economic models, resource allocation frameworks, and risk assessments are similarly evolving, incorporating lessons learned from solar system colonization efforts and adapting them to the realities of interstellar travel. Each theoretical proposition is rigorously debated and validated through a combination of astrophysical observation and computational physics. The pursuit of deep space colonization also fuels innovative engineering paradigms. Modular spacecraft designs, endowed with self-repairing materials and AI-managed systems, embody a shift towards resilient infrastructure capable of long-duration missions. Interdisciplinary teams evaluate scenarios including time-dilated travel, habitable zone transitions, and the potential for in-transit life support regeneration. In essence, the exploration of exoplanets pushes the frontiers of science and engineering, fostering a synergy between theoretical astrophysics and practical mission architecture that continuously redefines humanity's ambitions in space colonization. Looking ahead, researchers are exploring novel propulsion technologies and closed-loop ecosystem designs that can sustain human life for decades on distant exoplanets. Detailed feasibility studies require integrating precise orbital mechanics, energy conversion efficiencies, and advanced material sciences to mitigate risks. This integrated framework fosters collaboration among astrophysicists, engineers, and biologists, collectively propelling our ambitions to make interstellar travel a tangible reality. These coordinated efforts promise to bridge the gap between science fiction and interstellar infrastructure. Developing the technical infrastructure for space colonization demands breakthroughs in propulsion, life support, and habitat construction. Advances in nuclear thermal propulsion, solar electric propulsion, and ion engines drive the development of high-efficiency space travel, Yet each technology presents unique challenges that require precise engineering trade-offs and rigorous testing protocols. Moreover, designing closed-loop life support systems capable of recycling air, water, and nutrients indefinitely remains a critical area where bioregenerative methods and synthetic ecosystems are under research. Recent progress in material science has yielded radiation-resistant composites and adaptive shielding technologies, further enhancing habitat safety. Simultaneously, societal challenges loom large, as ethical, political, and economic considerations directly influence the feasibility of off-world settlements. International regulatory frameworks, property rights in space, and risk-sharing among nations and private entities are subject to ongoing debate. The balance between public funding and private investment in large-scale space missions creates complexities in project management and resource allocation. Furthermore, emerging technologies such as blockchain and decentralized decision-making have begun to reshape collaborative models for multinational space missions. Cultural factors also play an integral role in shaping the future of space colonization. Public perception, media representation, and the interplay between science and popular culture affect governmental policies and funding priorities. This multifaceted dialogue involves rigorous cost-benefit analyses, forecasting models, and scenario planning, all of which are underpinned by data-driven approaches. In particular, quantitative risk assessments and statistical models guide the implementation of safety measures and contingency protocols for long-duration missions. In addressing these technical and societal challenges, interdisciplinary collaborations have become indispensable. Engineers, scientists, economists, and policymakers must work together to integrate technological innovations with robust social frameworks that ensure the sustainable and equitable development of space colonies. This convergence of expertise seeks to establish not only effective colonization strategies, but also adaptable governance models capable of resolving disputes and ensuring long-term operational success. Robust solutions require continued investments in research, iterative design tests, and global partnerships that harness the combined expertise of multiple disciplines, ultimately driving transformative progress toward a future where space colonization transcends theoretical ambition to become a practical, realized achievement, truly empowering humanity's next leap. This detailed exploration of space colonization chronicles the remarkable evolution of humanity's ambitions from early theoretical visions to advanced technological blueprints. The journey, spanning Mars colonization, exploration of other celestial bodies, and the emerging focus on distant exoplanets, highlights the relentless pursuit of knowledge and the strategic deployment of cutting-edge innovations. It encapsulates decades of scientific inquiry, technical trials, and policy debates that collectively shape our expanding horizons beyond Earth. Our discussion has dissected the highly technical components of colonization strategies, including propulsion advancements, habitat design, and autonomous resource management systems. Detailed empirical data from robotic missions on Mars and other bodies have provided critical insights that underpin the engineering and economic frameworks of off-world settlements. These frameworks are continuously tested through sophisticated simulations, iterative design processes, and risk assessments, all of which inform the planning of future missions. Humankind's progress has not been without challenges. The complexities of deep space travel, the rigorous demands of sustaining human life in isolated environments, and the intricate interplay of political and societal factors require an integrated approach. The collaborative efforts between international agencies, private enterprises, and academic institutions inspire comprehensive strategies that address both the technical and ethical dimensions of colonization. The emphasis on adaptive governance and resilient engineering further assures that the vision for sustainable off-world communities is both ambitious and achievable. Looking forward, the future of space colonization lies at the intersection of empirical research and bold innovation. The continued convergence of astrophysical discoveries, technological breakthroughs, and robust policy development paves the way for a multi-planetary civilization. It is imperative that experts maintain a critical yet optimistic outlook, seeking not only to advance scientific understanding, but also to inspire future generations with the